Next, another PhD candidate in our group, Akhil, will be introducing us to some very recent work in balanced spanning tree construction.
Good evening, everyone. I'll talk about exascale algorithms for creating balanced spanning trees in subgroups. So this is the overview of my presentation. I'll briefly introduce the problem and motivate the need for exascale algorithms for process groups. I'll explain what process groups are. Then I'll tell the problem statement for the challenge that we are trying to solve, and then I'll talk about the two distributed algorithms that we recently developed. Finally, I'll conclude with some results. So process groups is, many parallel programs use process groups for expressing the communication amongst the processes. Process group is basically a subset of all the processes, and these are used often for collective operations and even point-to-point operations just amongst the members of the group. So the problem with the current existing methods to store and to create process groups is that they use a lot of memory. Basically the memory usage increases linearly with the system size, and this definitely is a scalability limit. And for example, in one of the recent reports by Balaji and others on MPI on 1 million processes, they reported that the number of MPI sub-communicators that can exist simultaneously dropped from 8200 at 1K processes to just 264 at 128K processes. So we analyzed many applications, and we find that many of the sub-communicators are used, or the process groups are used just for very simple collective operations such as reductions, broadcast, all reducing barriers. And examples of these are LU, quantum chemistry codes like open atom, histogram sorting, branch and bound, and others. In these collective operations like reductions and broadcast, the results are independent of the ranks from which the individual contributions comes from. So we use this feature to develop distributed algorithms. So in order to do these reduction and broadcast, balanced spanning trees are often used, so the problem here is, for example, we have an original spanning tree of all the processes, and we want to create a balanced spanning tree of just the participating processes, which here are the green colored processes. And the easiest or the centralized approach is to do an upward pass over this tree and collect the list of all the participating processes at process 0, select one of them as a root, and select k child vertices, split the remaining into k partitions, and send them to the child vertices and repeat the same process. So this is takes order n memory and also order n time. So the problem that we are trying to solve is to construct these balanced spanning trees without collecting the list of processes. So the first algorithm that we developed is shrink and balance. So in the centralized approach, what we were doing was just collecting the list of participating processes and putting them all together at process 0. So we do not want to do that because that takes order in memory. So rather than collecting, what we do is we use that information during the upward pass to do something. So what we are trying to do here is that we try to exclude the non-participating processes from this spanning tree and just have the participating processes. So in order to do that, we need to remove these red colored vertices, which we call as the holes here, and so we have to replace these holes by the participating processes. So one of the ways to do that is to use these green color vertices to fill the holes. So in order to do that, what we do during the upward pass is that each node sends as many leaves along during the upward pass as are needed to fill all the nodes along the path from its parent to the root. So each node can send a maximum of order log n nodes to its parent, which can be used to fill if any holes are encountered on the path to the root. So this shows a step-by-step demonstration of the shrinking process. For example, here after the first after a step at the leaves, the root this hole gets replaced by one of the leaves 7 here, and similarly, in this case, then after that here we are replacing the process 2 with one of the leaves 13, and similarly the root is replaced by another leaf. So a nice thing about this thing is that we can do this thing in the same time as a simple upward pass over the tree. So here we can see that these green colored bars show the entry methods of the upward pass, and the red colored bars, these small red colored bars are the relocation messages sent to these leaf nodes which are replacing the holes. So by the time the upward pass reaches the root of the tree, we already have this tree generated. Now once we have this spanning tree of just the participating processes, the task is to balance it, because it may not be balanced. And to do that, what we do is, the root node knows the size of the entire tree, and it can using that it can calculate the height of a balanced or perfectly balanced spanning tree. Now it can, based on that, it can also identify the maximum capacity of each of its children. Based on the height of the final spanning tree, it can calculate the capacity of each one of its child. Now after the upward pass, the root node also knows the size of each of its child, so it can calculate how many excessive vertices are present in each of its child vertices. Now if any of the child vertex has more vertices than its capacity, though that child vertex or the child subtree is referred as a supplier, and it can be assigned to other child vertices which have some remaining capacity left over. So basically the root node what the root node will do is, if it needs any vertex child for itself, it will request one vertex from one of the suppliers, and then assign the rest of the suppliers to its child vertices. The child vertices would then do the same thing as the root did. If they need any vertex, they'll request from the suppliers, otherwise pass on those suppliers to their children. The next algorithm is shrink and hash. In this, what we are doing is, after the upward pass, if the root node knows the size of each of its subtree, it can assign the ranges of ranks to its subtrees. For example, the root node here knows that the size of this subtree is 4. There are only 4 participating nodes from this subtree, and here there are only 3. So it can assign 0 to 3 rank to this subtree, and 4 to 7 rank to this subtree. So similarly, all the holes in between, they won't take any ranks and just pass on the ranks, and we can assign ranks to all the participating processes. This is another example in which here we did not shrink the tree, we just used the original tree. Here we are actually shrinking the tree and the holes are absent. So in the same way we can assign ranks here also. So the idea is that once the ranks are known, each process can calculate the rank of its parent and children using some simple calculation. And once the parent and children ranks are known, we can use hashing to get the process IDs corresponding to those ranks. And that is done by simply mapping a rank I to a process ID hi using a hash function. Both the child and the parent can use the same hash function to contact the same process ID to obtain the process IDs of the parent and children ranks. So this is the performance of the two schemes. On the y-axis here is the execution time, normalized execution time. 1.0 corresponds to the time taken by the centralized scheme, and we can see that the hashing these are runs on 64K cores of BlueGeneP. The hashing scheme consistently performs. On the x-axis are the different subgroup sizes. The hashing scheme consistently performs better than the centralized scheme. The shrink and balance scheme it performs worse than the centralized scheme up to participation probability 0.1, but after that it outperforms the centralized scheme. One thing to note here is that the centralized scheme is message conservative. If we look here, that the number of messages in the balancing scheme, sorry, I mean to say the shrink and balance scheme is message conservative. The number of messages are almost the same as, very close to the number of messages sent in the centralized scheme, and the number of messages in the hashing scheme are much more, almost 2 to 3 times at certain sizes. But despite that, the hashing scheme is slower than the balancing scheme is slower than the hashing scheme, and the reason for that is that it has longer critical path, even though it is sending very fewer messages. These are the scaling results of these 3 schemes on BlueGeneP. At low scales and low probability, centralized scheme is slightly better than the distributed schemes, but the hashing scheme in most of the cases performs significantly better than especially at large scales, it performs significantly better than the centralized scheme. And the balancing scheme, it beats the centralized scheme at larger scales. There is certain room of improvement that we are still working on in the balancing scheme. Finally, to conclude that system ranked subcommunicators are sufficient in many scenarios. We have developed order 1 memory and order login creation time algorithms for process groups. These algorithms are significantly better than reference centralized schemes, and they are order of magnitude faster than MPI's communicator creation algorithms. Thank you.
Let's thank our speaker. Any questions?
Point out whether even when they are slower, they use much less memory.
Yeah.
That's
so
good. That was
all of them.
Yeah.
So are these methods used in some portions of Trump++ now, or is this still at the algorithmic stage?
Yeah, it's still at the algorithm stage.
Are there particular areas where these are anticipated to be used?
Given the increasing performance, we can make static construction.
Yeah, it might become a default going forward. So we're closing the workshop here.